Let's turn to anthropogenic climate effects. We start by a brief review of climate numerical modeling and global warming. Why numerical modeling? After all, we did describe energy balance equations earlier. In reality, the solar constant is not constant. The albedo changes with land use changes, ice melting, and cloudiness. The emissivity changes with greenhouse gas changes and cloudiness. We have a need to model the three-dimensional atmosphere at least. But the atmosphere interacts with land surfaces and with oceans. These are examples of observations that were not included in the Earth energy balancing equations earlier, and can only be best taken into account by numerical modeling. A climate system includes the atmosphere, hydrosphere, lithosphere, and biosphere. The climate system involves the exchanges of energy and moisture that occur among the 5 spheres as shown here. Climate modeling is an attempt to encapsulate everything we know about the Earth system. This involves the atmosphere, the oceans and sea ice, vegetation, biogeochemistry, aerosols in atmospheric chemistry, and more, along with all of the interconnections and feedbacks involved. The growth of computer power, plus our own knowledge of planetary systems, has allowed these models to become increasingly powerful. Climate modelings are computer-based simulations that use mathematical formulas or equations of some of the basic laws of physics and chemistry to recreate the chemical and physical processes that drive Earth's climate. These basic equations are conservation of momentum, also known as Newton's second law, force equaling mass times acceleration, conservation of mass, and heat flows between systems, including wind, currents, Gulf Stream, and more. Here are some of the key variables of global climate modeling, or GCM. We have temperature, wind vector, pressure, mass density, wavelength, energy flux, emissivity, mixing ratio, including greenhouse gases. Here are some of the fundamental laws of physics. Mass continuity, equations of motion or momentum continuity, thermodynamic equation or energy continuity, and chemical continuity equation, plus friction, gravity, latent heat, conduction, radiation, conservation of water vapor, chemical loss, chemical production, chemical species, and more. Both the atmosphere and ocean act to transport heat from equatorial regions to polar regions. Temperature gradients drive the weather. For day-to-day weather forecasting, we can ignore the ocean, as its conditions will not change in the next week. For longer timescales, we need to understand how the atmosphere affects the oceans and how changes in ocean circulation, such as El Niño, can feed back to affect weather patterns. To run a model, scientists divide the planet into a three-dimensional grid, or a generally squared grid, apply the basic equations over several time steps, and evaluate the results. All processes which take place on scales smaller than the grid scale must be parameterized. This is one of the major sources of uncertainty in using these models. Major examples include clouds, which is still the main problem, topography, and coastlines. This is one reason why global predictions are more reliable than regional predictions. Here is a specific example of the construction of the grid of the climate model. Here, the planet is divided into a grid of 5 squares. Each square is layered into tiles, each representing a precise sample of the ocean, land, or atmosphere. The climate data for a specific tile are fed into the computer. Data from adjacent tiles are factored in, and a climate model is created. And towards the bottom here, you see that there's effects on and from adjacent tiles. Computing demand increases inversely with square grid of horizontal resolution. From FAR to SAR, the grid is reduced by half, and the computation time is increased by about 16-fold. Computation memory and storage are increased by even larger fold. Let's repeat this. Computing demand increases inversely with square grid of horizontal resolution. From FAR to SAR, the grid is reduced by half, and the computation time is increased by about 16-fold. Computation memory and storage are increased by even larger fold. Increased computing power has allowed increased resolution. So what are we looking for? A major focus is on global mean temperature. Rainfall. How is it distributed spatially and seasonally? Does it come as more intense downpours? Is it likely to rapidly re-evaporate due to higher temperatures? Changes in winter storms or tropical cyclones? In temperature, will there be more heat waves, that is, periods of several days that are too hot, or other extremes? Models are tested to see if they generate past known climate patterns. Atmospheric models calculate winds, heat transfer, radiation, relative humidity, and surface hydrology within each grid and evaluate interactions with neighboring points. Again, climate models use quantitative methods to simulate the interactions of the atmosphere, oceans, land surface, and ice. Here, you can see a comparison between modeled and observations of temperatures rise since the year 1860. You have A, natural forcing only, B, anthropogenic forcing only, and C, natural and anthropogenic forcing. We have good agreement between modeled and observations of temperatures rise since the year 1860, only when both natural and anthropogenic forcings are taken into account. This is another way to confirm the accuracy of the modeling and the rise in temperature in the last 100 years or so. Let's turn to climate prediction. To predict the climate in the year 2100, we run the best climate models available. To do this, we need to decide on the conditions which are significant, much like the composition of the atmosphere, over the next 100 years, and run the model for 100 years of computer time. Since we can't know in advance what will be the atmospheric conditions, we use scenarios, or SRES. For example, the CO2 content of the atmosphere in the year 2100 depends on inputs and outputs between now and the year 2100. Thus, we need emission scenarios and a good understanding of the carbon cycle. IPCC refers to the Intergovernmental Panel on Climate Change. SRES refers to the Special Report on Emission Scenarios prepared by the IPCC. These scenarios are generally indicated by acronyms such as A1, A2, and so forth. Here are examples of scenarios. In A1, this is a future world of very rapid economic growth, global population that peaks in mid-century and declines thereafter, and the rapid introduction of new and more efficient technologies. There are 3 subgroups, including fossil-intensive, or A1FI, non-fossil energy sources, or A1T, or a balance across all sources, or A1B. In A2, this is a very heterogeneous world. The underlying theme is that of strengthening regional cultural identities, with an emphasis on family values and local traditions, high population growth, and less concern for rapid economic development. In B1, this is a convergent world with the same global population, which peaks in mid-century and declines thereafter, as in the A1 storyline. In B2, this is a world in which the emphasis is on local solutions to economic, social, and environmental sustainability. For the next 2 decades, these simulations suggest that a warming of about 0.2 degrees Celsius per decade is projected for a range of SRES emission scenarios. Even if the concentrations of all greenhouse gases and aerosols have been kept constant at year 2000 levels, the simulations suggest a further warming of about 0.1 degrees Celsius per decade. Rainfall will continue to become concentrated in increasingly heavy but less frequent events. The incidence, intensity, and duration of both floods and droughts will increase. The intensity of hurricanes will continue to increase, though their frequency may dwindle. Recent modeling attempts have tried to isolate the impact of anthropogenic versus natural forcing. Continued greenhouse gas emissions at or above current rates can cause further warming and induce many changes in the global system during the 21st century that would very likely be larger than those observed during the 20th century. In this photo, warming of the climate system is clear. Human-caused warming over the last 40 years is visible. Now we will talk about extreme weather events. We'll start with Mount Kilimanjaro. The decrease in the glacial area can be seen clearly in the satellite images of Kilimanjaro by comparing 1976 and 2006. Here is the image of Kilimanjaro in 1976. Here is the image of Kilimanjaro in 2006. Notice that the ice has almost disappeared. Now we will talk about Lake Chad. Here we illustrate the climate change impact on Lake Chad. Here is the satellite image of Lake Chad in 1972. Here is the satellite image of Lake Chad in 2007. We can see a continued decline in lake surface area from 23,000 kilometers squared in 1972 to only 300 kilometers squared in 2007. Hurricane Katrina, which took place during the 2005 Atlantic hurricane season, was the costliest natural disaster and one of the 5 deadliest hurricanes in the history of the United States. At least 1,800 people lost their lives in the hurricane and the subsequent floods. The European heat wave in the summer of 2003 caused massive loss of life. The deaths of at least 77,000 people have been attributed to the heat in one summer. Heat waves of 2010 were centered on Western Russia. It surpassed the 2003 heat wave. From late July until the second week in August of 2010 in Russia and Eastern Europe. In Moscow, the daytime temperatures reached 101 degrees Fahrenheit, or 38.2 degrees Celsius. In Kiev, nights reached 77 degrees Fahrenheit, or 25 degrees Celsius. Crops were destroyed. Fires swept across western Russia. And estimates now put the Russian death toll at 55,000. The 2010 Pakistan floods began in July of 2010, following heavy monsoon rains in the Khyber Pakhtunkhwa, Sindh, Punjab, and Balochistan regions of Pakistan. The estimates are that more than 2,000 people died and more than 1 million homes were destroyed. Climate change is predicted to have a range of serious consequences, some of which will have impact over the longer term, like sea level rise, while some have immediate impacts, such as intense rain and flooding. The latter are obvious and easily grasped by the public at large, thanks to the Internet, which makes the images of these events available to the 4 corners of the globe in a matter of minutes or hours. The question about these extreme weather events we've just described is whether they are caused by natural climate forcings or human forcings. In other words, can the Global Climate Model, also known as GCM, shed light on possible links between these events and anthropogenic greenhouse gas emissions? Before we attempt to answer this question, let's group extreme weather events into 3 categories. Category 1 is extreme temperature highs, which includes heat waves. Category 2 is high levels of precipitation and associated flooding, including the lack of precipitation and associated drought. Category 3 is storms, including windstorms, hurricanes, and more. Increasing high temperature extremes are among the easiest to identify. The GCM suggests that cold and warm extreme temperatures are rising globally. In Europe, daily high temperatures are rising more in summer than in winter. And warm extreme temperatures are rising twice as fast as cold extremes are warming. There are fewer deaths from cold and more from heat. Here is an animation of the results of climate modeling on regional scale instead of global scale. After all, the climate change affects humans and the biosphere in general on a regional scale. The temperatures are indicated here in Kelvin. The modeling year goes up to the year 2100. The animation includes a year-running indication in the temperature scale. This animation is based on a moderate CO2 emission. It gives us an indication of future climates. Notice the appearance of orange color, which indicates warming at the beginning of the century with hotspots of warming in the Himalayas and the Arctic Ocean as the ice melts. Notice also the warming differences between lands and oceans. The air in oceans remains relatively cool over the years compared to the air in lands. This animation shows that in the middle of the century, we will have an orange color covering almost all continents, again indicating warming. By the end of the century, the temperature will have increased by more than 10 degrees Kelvin compared to the present temperature. This increase is indicated by the yellow color in this movie. Let's repeat this. The animation includes a year-running indication in the temperature scale. This animation is based on a moderate CO2 emission. It gives us an indication of future climates. This figure shows a comparison of observed continental and global scale changes in surface temperature, with results simulated by climate models using natural and anthropogenic forcings. Decadal averages of observations are shown for the period 1906 through 2005, indicated by the black line, plotted against the center of the decade and relative to the corresponding average for 1901 through 1950. Lines are dashed where spatial coverage is less than 50%. Blue shaded bands show the 5 to 95% range for 19 simulations from 5 climate models using only the natural forcings due to solar activity in volcanoes. Red shaded bands show the 5 to 95% range for 58 simulations from 14 climate models using both natural and anthropogenic forcings. The magnitude of the rise in mean temperatures and the existence of severe extremes, such as the European heat wave in the summer of 2003, are inconsistent with natural cycles, and the most plausible explanation is climate change. These changes are consistent with the model influence of anthropogenic greenhouse gases, enhancing confidence that the phenomena is indeed largely attributable to human forcings. There will always be natural variability, and some places and some years will be warmer or cooler than average. In general, however, summers will get hotter, not only because of higher temperatures, but also because humidities will increase. That means that heat waves, like the one that killed over 77,000 people in Europe in 2003, will become more common. On the plus side, winters will be warmer in many places, reducing heating bills, and the number of days with frost is likely to decrease. The analysis of Stott and colleagues in 2004 suggests that it is very likely that human forcings have already at least doubled the risk of the 2003 heat wave occurring again. Now, let's talk about floods and droughts in the context of global climate modeling. Providing the link between climate change and precipitation levels and resulting flooding or contribution to drought is more difficult than for heat waves. Precipitation and flooding are periodic phenomena, making patterns and extreme events harder to model. Recent global climate modeling attempts are capable of isolating the impact of anthropogenic versus natural forcing. Isolating water vapor forcing may shed some light here. Drought is very easy to recognize, but only recent global climate models are able to distinguish climate change trends from natural variability. Precipitation changes imply droughts. Droughts are cyclical, and severe events can be expected every 10 years, with very severe events recurring, on average, every 40 years. The North Atlantic Oscillation is strongly influential. When in its negative phase, as it is now, it causes drier winter weather, and hence less recharging of rivers and reservoirs, exacerbating summer droughts. Recent studies suggest that the land area of the world affected by severe drought has doubled since the early 1970s. Half of this trend is estimated to be due to changes in precipitation, and half due to warmer weather. Now, let's talk about storms, including hurricanes, cyclones, and monsoons, in the context of global climate modeling. While trends for temperature and precipitation are somewhat more clear, the picture for the intensity of windstorms is just emerging, and results seem to vary in different regions of the world. Recent studies indicate that the increased frequency of storms is still probably due to natural cyclical variation. Measurements show a noticeable rise in sea surface temperatures, which are a main determinant of the strength of storms, as well as the total column water vapor and the available convective potential energy. Studies show that the total number of hurricanes has not changed. However, the intensity of hurricanes has increased. Nowadays, we have more Category 4 and 5 hurricanes and cyclones than before. This change is probably due to higher sea surface temperatures. It is difficult to know whether this trend will continue. Monsoons are particularly sensitive to global temperature change because they are driven by the contrast in temperature between water and land. The numerical modeling suggests that Sahel Africa may get wetter with a reduction in temperature by 1 degree Celsius, and Asian monsoons may get stronger and stormier with 2 degrees Celsius temperature increase. Now, let's talk about mitigation and adaptation to climate change. Mitigation, or avoidance, here refers to measures to reduce the pace and magnitude of the changes in global climate being caused by human activities. Adaptation here means measures to reduce the adverse impacts on human well-being resulting from the changes in climate that do occur. Mitigation and adaptation are both very important. Let's start by talking about possible mitigation measures. We can reduce energy needs and encourage recycling. Accelerate the development of alternate energy sources with very little or no carbon, that is, wind, geothermal, hydro, solar, biomass, and more. For example, an increase in solar capacity by 1,000 times. We can capture and sequestrate carbon dioxide when fossil fuels are converted or burned. Halt deforestation, for example, increasing forest planting. We could accelerate the development of the fuel efficiency of cars, trucks, buses, trains, and aircraft. For example, doubling car fuel efficiency from 30 miles per gallon to 60 miles per gallon. Increasing the atmosphere's reflectivity by injecting reflecting particles into the stratosphere might be affordable and reversible, but would be likely to deplete the stratospheric ozone. Placing reflecting materials or mirrors in Earth's orbit or at the Lagrangian equilibrium point between the Sun and the Earth would be staggeringly expensive. Develop technological ways of cleaning CO2 out of the air, and you may add your own recommendations, but please, no giant space umbrellas. Now, we'll talk about possible ways of adapting to climate changes. You can avoid new ocean coastal development. Ocean coastal properties cannot be expected to survive routine future hurricanes. Avoid structures elevated below 28 feet above sea level. These structures are at risk of destruction by a storm surge. Locate new development higher than 110 feet above sea level, because 80 feet of sea level rise is likely. Also, as aquifer withdrawal continues to negatively impact irrigated landforms and sea levels rise due to ice cap melt and/or water thermal expansion, these storm surges will rise higher over time. Increase the use of light personal electromagnetic flying rigs. You could increase the use of electromagnetic powertrains for transit shipment and transport options. And here you may add your own regulations. To conclude, let's focus on a particular mitigation measure, which consists of capturing and sequestrating CO2. The aim of CO2 sequestration in sub-seabed geological formations is permanent isolation of CO2. The major steps are 1. CO2 separation, capture, and compression. 2. Transport to injection site. 3. Injection into geologic formation. The geologic formation must be greater than 1,000 meters depth. 4. Measurement, monitoring, and verification. CO2 requires better seal rocks than water, gas, and oil. To date, no leakage has been detected. However, the study has shown that after the carbon dioxide is sequestered, the chemical properties of the water and the dissolved inorganic carbon change. Changes include 1. Sharp drops in pH. 2. Pronounced increases in alkalinity. 3. Significant shifts in the isotopic compositions. Also, it is shown that the CO2 can degrade carbonate substances in the rock. Here are some problems I advise you to do to better assimilate the materials. Remember, there is a large selection of iMode education lectures, which can further enhance your knowledge of earthquakes, volcanoes, climate, and energy. Thank you for listening to this iMode education lecture.